And we move on to the next talk. I see he has to get ready. So next talk will be given by Sebastian from IBM Research Zurich. And as we know, IBM Zurich is one of the sources of great ideas. I don't need to mention the Nobel Prizes which went there. So we are looking forward to hear what Sebastian will tell us. And his talk will be on revolutionizing deep learning through in-memory computing, an overview and future prospects. Please, Abu.
Okay. Yeah. So good morning, everyone, and thanks, Rainer, for the very kind introduction. It's a real pleasure to be here in this conference, in this very multidisciplinary venue. So my talk, as you can see, is on deep learning, in-memory computing for deep learning. And already I've heard a lot from many illustrious speakers in the last couple of days on this topic. So hopefully I can bring in some additional industrial research perspective to the topic. So this is the agenda for today. So first, I would like to talk about what has been done. I don't know how many of you know this place. Anyone? So this is supposed to be Valseberg. This is the tallest point in the Netherlands. So that is probably where we are right now with the field. And so I just want to talk about about that, where we are right now. And so what next? So having said that, I believe that the technology has so much merit that we could reach my favorite mountain, which is basically Matterhorn. And what I'll show in the second part is the kind of steps we are doing towards reaching that goal. And then finally, I want to point out that this is not just an area which is all set and it's all engineering, but there's also a bit of exploration that you can do. So that'll be the third. I mean, I'll just give a brief glimpse into some of the exploratory topics going on there. Right. So when you talk about the first part, so what has been done, right? So prior to that, I just want to give a brief overview of where in-memory computing stands in the context of AI hardware in general. So as was pointed out many times during the conference itself, deep learning is a machine learning paradigm which was actually born out of a desire to understand the human brain, right? So there's no doubt about it. So simple models were created of the biological neurons and synapses. And these very simple abstract models, when you scale them up to very large numbers, they are doing some remarkable things, as you have seen from the recent last decade. But one problem with these artificial deep neural networks always has been that the hardware realization was anything but neuro-inspired. So even though algorithmically it had strong neuroscience connections, from a hardware point of view, it was very different, right? Because if you look at the human brain, we have physically stationary neurons and synapses. We have less precise analog computation. Whereas all the attempts to implement these neural networks in traditional hardware, they were relying on systems where you have a physical separation between memory and processing. Of course, synaptic weights being stored in the memory, and then you need to shuttle them back and forth to the processing unit. So what was the price we paid for that? We almost lost 3 decades, right? So we had this so-called lost decades, where you had the algorithms ready, but we were not ready with the hardware, because we didn't have the computers fast enough to run the deep neural network algorithms. And even today, I would argue that one of the biggest roadblocks for further adoption of AI is going to be this fact that we don't have the adequate hardware. But having said that, we of course made a lot of progress, right? So we have come a long way from this traditional, von Neumann picture that I painted with this one processing core and whatnot. We have gone into very specialized digital engines with several of these processing engines. These are these PEs, as indicated in the diagram there. Then you have a lot of concepts came, a lot of conceptual breakthroughs, right? Massive parallelism being one, but also the fact that you can run deep neural networks with reduced precision. So that is another big step. Then, better data locality. You may want to add some memory right next to the processing unit. And finally, the realization that you don't need simple instructions, but you can work with more complex instructions. So all these things came together, and we are in that age of custom digital accelerators. So everybody is building their own custom digital accelerator. And IBM was, in fact, one of the pioneers of this effort. In fact, there was one of these papers in ICML in 2015 that kind of brought forth the whole reduced precision arithmetic work. So what is IBM doing in this space? So IBM has a neural processing unit embedded in IBM's mainframe chip, the Telum processor. So that is what is seen here on red there on the top one. So that's what you call an on-chip accelerator, what you would call. We also have recently built a larger scale system that's called the Artificial Intelligence Unit, which comprises of many such processing cores. And there's also this chip called North Pole, which probably many of you heard about, right? So this appeared in ICNCE last year, which in my view is kind of the limits of what you can do with this kind of distributed computing that I talked about, right? So it's kind of, if you had pushed these digital accelerators, that's probably where you can arrive at. That was an 800 millimeter square chip built for that purpose. So these are all these custom digital accelerators. So now comes the fundamental question, right? So where are the limits? Why should we change course? Why should we do something else? And the question that we would like to answer is it possible to build a highly performant accelerator? So I'm not interested in edge acceleration or whatever, right? A highly performant accelerator that can operate with this less than 10-watt TDP. So in my dream, it's like you take the GPU up there, which is in the 100 watts. And as was also pointed out by the previous speaker, now we are in the 2 kilowatt kind of regime with chips. Can we take that thing which costs around 100 watts, $10,000? Can we shrink it to 10 watts and maybe less than $100, maybe even $10, right? So what is the problem there? So let's look at the empirical evidence of what's going on here, right? So there is this very nice chart which is produced by the folks at the MIT Media Lab, where they take all the accelerators that are being built, and then they plot in terms of the peak performance versus the peak power. And what you see is that whether you are in the low power domain or whether you are in the system level, all these accelerators, they all face this sort of brick wall, which is 10 tops per watt or 100 femtojoule per operation. So this means that if you really want to have a very high-performant AI accelerator, then the only way in which you can do is to go in this direction. So what you're doing is you're increasing your overall power budget so that you can run larger and larger neural networks. So it looks like that's the only trick in town these days, right? And it's not surprising why we have this 10 tops per watt or 100 femtojoule per operation barrier. It's all coming down to the data movement problem again. So even if our processing engines are consuming zero energy, just the fact that you need to move data from the external DRAM to the chip or from SRAM itself to the processing engines, you have reached this 100 femtojoule per operation or the 10 tops per watt barrier. So what it all points out is the next conceptual breakthrough, if you want to have, has to be in-memory computing, some form of in-memory computing, right? You have to compute in memory. You cannot afford to move around synaptic weights. And so in-memory computing, as you know, is essentially that, right? It's a broader paradigm which says that you can perform certain computational tasks in the memory array itself by exploiting the physical attributes of the memory devices or the way they are interconnected, the array-level interconnection, right? And as you very well know, very many different types of memory devices can be employed to perform in-memory computing. But let's now focus on in-memory computing in the context of deep learning inference. So when you talk about in-memory computing for deep learning inference, the fundamental entity that you want to realize, I would like to call it the in-memory MVM core or the in-memory MVM abstraction, is to build that circuitry there, right? So you see this circuit there, which will perform y is equal to wx. So you would like to construct this kind of a system in whatever means it is. I don't care how exactly you build it, but someone has to build me this entity here. And of course, one prominent way of doing it is the resistive crossbar array that we heard multiple times about, right? So you basically arrange resistive memory devices in a crossbar configuration, and then if you now program the conductance values as proportional to the weight values, then you can perform this MVM operations in memory, and the current that you measure here, when you bias them all together, would be proportional to the result that you're looking for. So very simple, right? That is the Ohm's law and the Kirchhoff's current summation law giving you that, that MVM abstraction that you're looking for. Now, once you have that in-memory MVM core, then of course you can sync them up together. You can all collect them together. And then what you could do is you could program a neural network. So you pre-train the synaptic weights. You map them into these memory devices. And then each of these in-memory MVM cores, they'll be performing the matrix vector multiply operations. And then they'll be shifting around the activations across the cores. So this is exactly like how the biological brains work, right? So the activations are like flowing through a physically laid out synaptic array. So that's all it is to it, right, when you talk about deep learning inference. And if you have now full weight stationarity, if you can store all the weights on chip, then you can perform deep learning inference in a very efficient manner. But where do we stand with this in-memory MVM technology, right? How do we build this in-memory MVM core? There are many different ways in which you can do it. For example, you could take you can have a very simple, what you call digital in-memory computing, where you use SRAM devices to store the synaptic weights. You can perform the multiply operations using some logic operation. You can sum up the results using a distributed adder tree. So this is what you would call digital in-memory computing with SRAM. And there are many startups like Accelera AI, D-Matrix, which are all working on that concept, right? So here we're using conventional digital SRAM to do that. Then there is another approach whereby you don't want to do digital approaches, but you could just say, I don't want to do this digital adder tree. I just want to accumulate it on a wire by using something called switch capacitors and doing a charge sharing. So that is what you would call analog in-memory computing, just to be clear, right? So you start processing with analog instead of digital, but still it's in-memory. Then, of course, there is the resistive RAM-based approach, but in reality, what you do is you don't modulate the voltages, but rather you would encode your input into the durations of the signals, and then you will integrate the current over a certain period of time. This is the most prominent approach, and yesterday you heard from Changfei, for example. Their company uses something like that to perform in-memory computing. And if you are in this mode, while you are at it, you could also use flash memory. Why? Because if you take flash, then if you bias it, if you program the flash in such a way that you, for a certain gate bias voltage, you modulate the current based on the weight value, then you can do the exact same trick as what you do here, right? You again apply input in terms of durations, you integrate the current, and then you get your get the result that you're looking for. So as you can see, in-memory computing can be done with a lot of memory devices. That's kind of the message here, right? And here, what you see here is probably the commercial landscape, at least in the startup space, of what is going on with in-memory computing. Right, so not even that, right? You can even do in-memory computing in the photonic domain, right? For example, you could take a photonic waveguide. You can put patches of phase change materials on top of it. Now, depending on the phase configurations that you have there, you can modulate the transmission through the waveguide. Now, if you connect them up into a crossbar array, then you can again do the whole operation in the photonic domain. So why would you want to do it in the photonic domain? Because it's extremely fast, right? Because you can modulate in the 10 gigahertz range, and you can also do the wavelength division multiplexing. So that means that you can have multiple MVM operations done at the same time, so by encoding on different wavelengths. So as you can see, there's even a photonic equivalent to in-memory computing. Right, so finally, how would you now go ahead and make an accelerator? So when you make an accelerator, it is not just this in-memory compute course that you're interested in. You want to connect them up with a lot of other entities, like you need some SRAM buffer, you need some digital processing units. So in the end, you're looking at a heterogeneous compute unit. Now, if you zoom into one of these in-memory compute core, it of course has a crossbar array, but in addition, you need the data converters, you need some control logic, you need some digital processing, and so on and so forth. So this is the full accelerator vision that we have. So it's never a full analog system, but in-memory MVM is just a part of that big vision that we have. So it's actually a heterogeneous system that we're looking at. Now, so what did we do in the last few years is really try to see if we can build such a heterogeneous architecture in IBM. So we fabricated two chips. So one of them was fabricated in fact, both of them were fabricated in 40 nanometer CMOS technology node. It's a FinFET with embedded phase change memory as the memory element. And so one of the chips, it's called the IBM Hermes chip. It has 64 tiles, 256 by 256 crossbar arrays. The ADCs are integrated per tile. We employed a digital communication fabric, so it's a mixed signal chip. And we also had an experimental chip where we had 34 tiles with 512 by 512 crossbar arrays, where the ADCs were not integrated per tile, and we were using analog computation, right? So both these chips were tried or were built to try out different concepts, but increasingly it's clear that a mixed signal approach is probably better, right? So currently our focus is mostly on a mixed signal, a Hermes-like architecture, which I'll talk about more in detail. So when you look at the Hermes type of architecture, so this is what it is, right? It has 64 cores, and they are all interconnected by a digital compute fabric here. And then if you zoom in into each of the tile, you can see that it's a 256 by 256 crossbar array of synaptic unit cells. And each synaptic unit cell now comprises of 4 phase change memory devices. So totaling 16 million phase change memory devices on chip. And it also has this on-chip local and global digital processing, as well as the communication fabric that I talked about. Now, again, without going into too much detail, how we encode weights is really in terms of the analog conductance values. So we have these devices, the 4 devices, organized in a differential configuration, 2 devices for positive, 2 for negative. And whenever you have a synaptic weight you want to map onto it, you would like to translate that into a conductance value, then you will achieve them by modulating the phase configuration within the memory device, right? So true analog storage. To achieve that value, we do typically iterative programming to program the devices to a certain target conductance value. And we also innovated heavily on ADC, because as you know, ADC is one of the key components, right, for this whole thing. So we conceived a concept of current-controlled oscillator-based ADCs, which are extremely compact, as you can see. That means that we can operate 256 of them in parallel. That means we can do the read operations together. So the essential idea of the ADC is just that you will translate the current which is coming in to a oscillation, and then you count using a digital counter, right? So that was the key idea there. And then when you put it all together, you can perform MVM operations per tile. In this case, you feed in like 256 vectors, 256 dimensional vectors. So in this case, 2048 MVM operations were performed. And this is the output. And if you look at it, you see that it's not a straight line, which means that there is some imprecision associated with the computation. And when you work out the math, you figure out that it's around 3 to 4 bit equivalent precision that we're looking at here, right? Whereas the accumulation is done in full precision because your current is being summed up along the wires. Okay, so if you now come down to Zurich, I strongly encourage all of you to maybe come and visit us. We have a software stack which can absorb networks, which can automatically map it onto the Hermes chip and run experiments. So here I will quickly show you a demonstration of Julian performing one of those cool experiments. So let me see if it works.
So we've prepared a small demo for you to showcase the capabilities of this new chip, which is a transformer model, a neural network that was trained to predict chemical reactions. So as input, you get a bunch of chemical compounds represented in the so-called SMILES notation, which is represented here. And then in the end, the transformer creates this output string here, which is then again converted into a chemical compound and displayed. So the chip is already programmed, everything is set up, I just need to run it. Now when I run it, you should see some activity of the chip. You can see some activations there. And after some time, we should see first the ground truth, what it should be, and then also the prediction of the chip, which, as you can see, matches the ground truth.
Yeah, so it kind of shows the sophistication, right? So you can actually take an arbitrary neural network, you can automatically map it onto this 64-core chip, and you can run experiments. So it really shows how mature the technology is. Right, now, so the second part, I want to talk about what next, right? So when you look at in-memory computing, we need to innovate on all these fronts here. So we have the basic memory technology, we have the AMC core, we have system-level architecture, and we have the software stack. So when you look at the memory technology, the current focus is squarely on compute density, precision, and improving the weight capacity. So when you talk about in-memory computing, you have to keep as many weights on chip as possible, right? So weight capacity is of paramount importance. In the periphery, I already mentioned the ADCs, but there's also a lot of progress on how to make it even more energy and area efficient. In the system-level architecture, it's all about how we optimally design the various heterogeneous compute units and how do we organize and orchestrate the various components, right? That's the whole idea. And then at the top level, it's about how would you compile networks onto this chip, and how do we write software for these kind of new architectures. So I'll just quickly pull out a few of the examples that we're working on. For example, if you look at compute density, compute density, one of the key things, at least in the context of phase change memory, it's all about shrinking the dimension of the phase change volume. Because then your reset current comes down, which means that you can have smaller front-end transistors, you can pack more of them. So a lot of focus is on that, right? So on nanoscale confinement of simple materials, this in fact was work that we initiated with Martin Selinger many years back. But of late, we have built many more prototypes based on these concepts. And the other thing which, not necessarily in the context of phase change memory, is that you may want to really go into 3D. Because if you want more capacity, I think 2D is probably not enough. You may want to go into the third dimension, and that's, again, something is extremely important going forward. Now, in terms of compute precision, yeah, we had this concept of projected phase change memory. The essential idea is to have a material segment which is in parallel to the phase change material, which will, in that way, you can, you don't have to pass current through the bad amorphous phase. You can kind of bypass the current and go through the, the material which is adjacent to that. And this way, we have shown that we can go beyond this 4-bit compute precision that we have, maybe 5, 6, up to 10, up to 8-bit. That is what we have shown. But it's quite challenging to reach maybe 8-bit, I would say. I mean, something like 5 to 6 is probably where we could end up. But it's still a very interesting concept. And again, what we are doing right now is to really combine these two, right? And some very interesting results in that direction. Now, the heterogeneous architecture, I won't talk too much about it, but I just want to tell you that it's a very difficult problem, right? Because you have many different analog compute units, you have many different digital compute units, you have all the IOs, you have all this stuff. So there are infinite different ways in which you could organize them, and you can orchestrate, the different operations across the different compute units. I think the only message that you have to take from here is that it has to be a heterogeneous system, right? Because there is always a neural network with operations which you can support, which you cannot support using analog in-memory computing. So that means that you need this heterogeneous fabric, and you should be able to now map networks, any arbitrary networks, into such a fabric. So that's the key message here. Now, also, I said that we train a network and we map it onto this chip. But in reality, you have to train it in a slightly different manner. It is not too different from what you do for reduced digital precision. So you have to make the synapses be accustomed to be operating in a noisy manner. And so that is what you do with this hardware-aware training. It's all done in software. Recently, what we did is we showed that this hardware-aware training can indeed work across a whole bunch of different types of networks, right? That was something which people are not aware of. Even bird-sized models can now be robust to this kind of synaptic noise. And this is what is published in this Nature Communications article here. And in order to further develop this algorithmic side, we have fully open-sourced the IBM AI Hardware Kit, which is a powerful tool to develop these kind of algorithms to do hardware training. I really want to point out that we also have now enabled real hardware access. So I really hope that people can make use of it. We have 1 million phase change memory devices that you can program in any way you want. It's an analog programmable device, and use it in maybe in spiking neural networks or any other context that you would like to do, right? So please go to this website and try to see if you can access this real chip, right, which is sitting in the Zurich lab, and then you can use it any different way you want. And please do contribute to the AI Hardware Kit as well. So in terms of like real commercial next steps, besides what we do internally at IBM, of course, we are always looking at the frontiers of what you can do with in-memory computing. There are two projects that I want to really point out. So one of them is, in fact, done with ST Microelectronics, which again came up in the previous talk, right? So they are one of the leading manufacturers of microcontrollers, and they have a very strong roadmap in having embedded neural processing units as part of their MP-SOCs, this this multiprocessor SOCs, right, that they have. So you basically have neural processing units which are part of the bigger chip. And what we are doing with them is to build an in-memory computing-based NPU, which is based on the ST's phase change memory technology, right? It's an extremely interesting approach that we are pursuing. We are also part of a more ambitious effort from DARPA, where we are really trying to see if we can improve the weight capacity, right? I had this initial dream of maybe, having a very performant chip at the footprint of maybe a thumb drive, right? So maybe something like that. And so that's something like that where we are going at with this DARPA project that we are involved in. Right, so these are the two big government-funded projects that we are currently working on. And finally, in the last part, I want to talk a little bit about a bit more exploratory topics, right? So one of the things that people have always been suspecting with in-memory computing is that if you work on a intrinsically stochastic system, right, a non-deterministic system, then it may have better adversarial robustness, right? So we want to test this hypothesis, and we did a very thorough study of this effect on the IBM Hermes chip. For example, we tested all these different, all these standard benchmarks for adversarial robustness, and we consistently found that in black box attacks, for sure, the network was behaving extremely well, right, compared to any digital implementation or even reduced precision digital implementation. But what was also quite interesting is that it was adversarially robust even when you had white box attacks. That is, when you know the hardware, even then, because it is intrinsically stochastic and non-deterministic, it's very difficult to find attack inputs, right, because of that reason. And so we also could show that even in the case of hardware in the loop attacks, we have significant adversarial robustness. Now, going even more crazy to some extent, the question is it possible that with the same physical hardware, we can do inference on two different inputs? Can we compute in superposition? So this is what we tried to answer with this NeurIFS paper last year, where we showed that if we can create a separate superposition channels, by some kind of a key binding, unbinding kind of approach, then you can indeed pass multiple inputs through the same neural network and get the result simultaneously, right? It's extremely interesting, and we showed it in that paper for both CNNs and for transformers. And it's something, again, we are really working on even more. So again, very interesting ideas, which I think will also be very interesting going forward. The other very interesting topical area that we are looking into is, if you look at in-memory computing, it's not by any means limited to deep learning inference alone. We can even implement approaches which are going beyond a conventional deep learning inference. And for example, there is always this interest in combining deep learning with symbolic AI, mostly because of scenarios such as this, right? So when you have your Waymo car being stopped by someone wearing a stop sign T-shirt, it's not a good sign. So you may want to avoid some of those scenarios. And that is why we try to combine neural networks with symbolic logic. In this case, vector symbolic architectures. We found it to be a very good match because they talk the same language, and we can train them end to end. So if you want to know more about this particular project, you can, of course, go to this link and then read more about it. But what I want to talk in this context is that there are many VSA operators, such as superposition, such as similarity search, such as factorization. All of them can be enabled, again, using in-memory computing, right? So there's a very nice marriage between neurovector symbolic architectures and in-memory computing. And finally, again, it was pointed out many times in this conference that if you take, you can make or you can enrich your deep learning by feeding it with a lot more bio-inspiration. For example, you can add neuronal dynamics, you can have synaptic dynamics. There were a lot of talks on dendritic computing, for example. Of course, spike-based communication is a big deal. So what you see is that IMC can natively support many of these additional compute primitives, such as incremental weight adaptation that was shown by Robert in his talk, as well as synaptic dynamics at varying time scale, which we studied in this Nature Nanotechnology paper. So you kind of see that you can go way beyond conventional deep learning inference in this manner. Right, so that brings me to the summary of my talk. So my first point is that in-memory computing is arguably the only way where you can have large language models run on a thumb drive size systems, right? That's kind of the North Star for the research. And talked about the advanced prototype chips that we fabricated at IBM Research. I think the main purpose were twofold. One of them is that to show that the whole technology works, right, in real. And the second one was to show that you can seamlessly combine analog with digital. That's a very important step when you talk about in-memory computing. A lot of work going on in the space of improving the density and capacity of memory devices and the compute precision on the peripheral circuitry, heterogeneous architectures, and also the custom training libraries and compilers. I mentioned the two key government-funded activities that we are involved in, one in Europe and one in the US. And I just kind of gave a glimpse of some of the exploratory research efforts that you could do in this space. So before I conclude, I just want to kind of point out a few lessons that I learned, because I've been running this program for the last, 4 or 5 years now, and we learned quite a few lessons along the way, right? So the first one is that in-memory processing is the conceptual breakthrough, right? So the whole idea is that you have to process in memory. Because people keep coming to me and asking me, is PC RAM the solution? Is RE RAM the solution? Is Flash the solution? No, it doesn't matter, right? I mean, as long as you are performing the computation in memory, whether it is digital or analog processing or the type of memory device is more or less a detail, right? So that's one thing that we learned quite fast. The other thing is, it seems like people are looking for energy efficiencies of much larger than 100 TOPS per watt at the IMC core level. That's probably not even needed, because when you run a true neural network, you are almost always going to be limited by something else. It's sort of like the Amdahl's law that you have, right? So beyond a point, it doesn't really matter. So if you can get 100 TOPS per watt, and if you can have a lot of weight capacity, I think that should probably be enough, right, more or less. I mean, again, I want to point out that I'm not trying to build a brain like Kobena, right? These are talking about running an LLMs, on a device like that. Then the other point is the full weight stationarity is highly desirable. So even if you have a memory technology like SRAM, where you can reprogram the SRAM, right, it incurs some cost. So you would like to keep your weight stationary as much as possible, even if your memory allows you to be reprogrammed, right? That's another thing that's extremely important. Then I always see that digital is a villain, right? It's not. I mean, embrace digital processing when required, because, see, in advanced nodes, digital is actually a very big advantage. So if you can do something in digital, please do so, right? So that's also why in the ADC design, we went for more digital designs. We started using digital counters, for example. So it's extremely useful. And finally, programmability and the ease of deployment should not be an afterthought, right? Because when you start designing, think of how you would program it, how you would deploy it. I mean, often, like as scientists, we are driven into crazy ideas very soon, which may not have a practical relevance. But I think sometimes you have to step back and see whether we can program this device in a very easy manner and use it. Yeah, so before I conclude, I just want to thank the contributors. I mean, in particular, the team at IBM Research Zurich. I mean, they did the majority of the work, but we also worked very closely with our colleagues in the various IBM research labs, and also several academic collaborators, right? I mean, mostly in Europe, as you can see. And I would also like to thank all the funding agencies for generously supporting this program for many years now. And also the IBM Research AI Hardware Center, which kind of helped us with all the fabrication efforts. So that was a heavy lift. And before I conclude, I also want to have a personal thanks to Rainer Wasser. I mean, I mean, I think I wish him all the best for the next phase of your life. I think Rainer was always a humble person in my view. I mean, you're always like, I write to him something and, I get a response instantly, and I always wonder how he did that. I am sure he was working incredibly hard to make sure that happens. So he was always a great role model, as, it also showed that, you can be a great scientist and a good person at the same time, right? So that's something that was very nice about Rainer. So thank you, Rainer, for all your services, and thank you for inviting me over.
Yeah, Abu, thanks a lot for these very kind words, and of course for your very nice talk, which is now open for discussions. So I see the first one who would like to raise a question.
Hello, very nice talk. Thank you, Mark from Rossum, University of Nottingham. I was wondering about, sorry, it's a bit of a long question, but hopefully it's useful also for the wider audience. There's a certain trade-off when you start increasing the size in transformer models. So if a small network and you want to change your task, you typically have to retrain, reset your memory, and start from fresh. The bigger your model gets, the less retraining you have to do, right? I mean, in principle, you don't need any updating of your memory once your model is big enough. So there's a sort of trade-off there between the ability to reprogram your network and the size of your network. So where do you think this is going in terms of hardware and energy? I mean,
Yeah.
do we still want programmable memories in the end, or do we want to have only a very small set of programmable memories, or is it just is that going to turn out to be a very inefficient solution, and will it turn out to be much better to have more programmability at the cost of, but also using smaller networks?
Yeah. See, I mean, I don't think it is about big versus large. I think it's about how over-parameterized your model is. I think that is the key, right? So what you see, for example, is Llama 3, 3B, Llama 3, I believe 8B is almost as capable as, Llama 2 70B, right? So I think the existing LLMs are heavily over-parameterized, right? So the fundamental question is, okay, if you now shrink them to the right dimensions, to the amount of data that you have seen, right, then it's not very clear if it is still robust. So I think the jury is still out on that. So we have a program internally to evaluate networks of billion parameter and above to see how robust they are to analog noise. But this has to be carefully studied. We shouldn't be drawn with the conclusion on some highly over-parameterized network thinking that holds, right? So the real test is, whether you can still be robust with the 3B model as opposed to the 70B. I mean, but you're right that if you go to the 70B model, you're probably more robust, right? Just because it's over-parameterized. So you're right. I mean, but yeah, I think you're right. I mean, increasingly it shows that these larger models are probably more robust, and that is good for our field, right? But I would still wait a bit to see how over-parameterized they are.
Thank you.
Next to it.
Hi.
Next question,
this
please.
is Chirag from Research Center Ulish. My question is related to in-memory computing for training. I asked this question specifically because in future, if the AI becomes profound in terms of continual learning, and especially knowing with the current research that non-volatile memory-based in-memory computing is not so apt for training, now, does it mean that we now have to get back to traditional computing systems, or what is the way forward if continual learning systems become profound?
Yeah, but you see, continual learning, you can do it in many different ways, right? So one of them is, of course, you touch the synaptic weights itself, right? But I kind of like the approaches where you have the synaptic weights. I mean, you have a neural part which is fixed, and then you have a adaptable external memory, like a memory augmented network kind of thing. I believe that that's a little bit more amenable to continual learning because training, touching all the synaptic weights, it's so complicated, and it is so costly, right? So I think we had a CVPR paper last year where we showed one such approach with an explicit memory that was doing very well. So we are currently working on a larger variant of that. Yeah, so, and there are, of course, approaches where you just turn the last layer, for example. But yeah, I personally, my favorite is to keep the neural network fixed and then change something else. right? Like, for example, have a explicit memory, associative memory, you can update it, you can change it based on the examples you have seen. In that kind of an architecture, it's probably a bit better suited, I would say. Yeah.
Can I ask an extended question? What is your take on capacitive-based in-memory computing architectures?
It looks interesting, but I mean, frankly, I haven't worked much on it. I know that there are quite a few people like Shimeng Yu and so on who are looking into that. Definitely, the fact that your signal is already in the voltage domain and you don't have to convert, right, from a current to voltage in some form is very attractive about it. But you see, I mean, one of the things which at least in my opinion, it is all about weight capacity, right? So as I said, I also said that we may want to go into third dimension. So, I mean, if there is a pathway to go into a third dimension with multiple layers, it could be interesting. But maybe that's something to look into. So because on the 2D, I mean, we are not that far away from SRAM in memory computing, to be fair. So I think we need to get that third dimension going.
Thank you.
Next question, please.
I'm Christian Lanius from Aachen University. Thanks for your talk. My question is, you say weight stationary and capacity is key or one important thing. With GPT-4 being in the trillion parameter range and no sign of stopping and scaling of networks, do you think there is, from what we know and can do today, a straightforward way to get there, or do we need a new breakthrough?
Do you know the weight capacity of your or thumb drive in square millimeters, sir? It's
is it terabit range?
It's 14 gigabit, yeah, 14 gigabit per square millimeters. So I don't think there's any physical limit. It's just about how much, how you engineer the system, right? So yeah, there are non-volatile memory technologies that have the capacity. And most of these AI chips are huge. We are talking about 800 millimeters square, or even bigger, right? So I think there is a pathway. It's not easy. I'm not saying that the first thing we'll do is like to put GPT-4 on the chip, but you can definitely put like a Llama 3B or a Llama 7B kind of networks on a reasonable size chip, I believe.
Thanks.
So next question. Yeah, please.
Hello, Abu. Thanks for the great talk. I really enjoyed it. So I'm Jimmy from Zurich. And I was wondering, so the whole point of in-memory computing, I guess, is to minimize the energy consumption. But as far as understood, the Hermes chip is purely inference, while the most of the energy consumption comes usually from the training, right? And so I was wondering how you would address the save of energy at training with in-memory computing.
I don't fully agree with that. I mean, I'm pretty sure that we have consumed more energy using ChatGPT than training ChatGPT by now, by far. Because I think the inference cost is huge. And yes, you train once, but then you use these networks over and over again. In fact, some of the internal market studies show that almost 95% of the effort is towards inference hardware. I mean, because the training, I mean, looks like we have one person who is doing it very well, one company, and we all seem to be kind of agreed to buy their stuff, right? But on the other hand, for inference, I think you have a lot of different scenarios where you may want to have it in the cars, or Industry 4.0, or edge device. I think there was also all these things discussed in the last meeting as well, last talk as well, right? So I think the inference market is actually pretty big, and deploying network is actually, I believe, a very, very serious energy-consuming thing. Yeah, I mean, imagine if you want to do, like, if your laptop, I mean, like, there's AI laptops which are popping up, right, where they do all the processing on the laptop. I mean, it's all about inference then. And then a follow-up question then. Then I guess the future work would be to also potentially, I mean, if you're on the other way, like considering that training consumes a lot of energy, I guess the future work would also to embed in-memory computing for training. And do you see your group in the perspective of training in the loop or whatever with your chip? I think training for small devices, I think there is definitely a case to be made, right, within memory computing, like on-chip. I think was also the question of about the continual learning, for example, right? Continual learning, small networks which learn on the fly in smaller device settings. But I really don't see how we can be competitive against a GPU when it comes to, training, because of the amount of, at least if we cannot find out a better way than, the traditional SGD backpropagation-based approach, I don't see a good pathway, because there is so much other stuff that needs to happen in training that in-memory computing can only deal with only a fraction of it. I think we estimate like 1/3 or something we can accelerate, but there is still this other 2/3 which is still troublesome. So yeah, so I think, I still haven't figured out whether there's really a market for, or there's really a pathway for in-memory computing when it comes to large-scale training.
Thank you very much.
So, last question.
Hi, great talk. I'm Richard Norte from TU Delft. And I was really, I really like that you mentioned these photonic networks because people like them for the low latencies and the energy savings, and that's also kind of the motivation here for the in-memory stuff. And so do you actually see a realistic role of photonics in any of these systems, or is this kind of just
I mean, photonics is very fascinating, right? I mean, 10 gigahertz modulation, like, that means you're doing 1 MVM operation in 0.1 nanoseconds, which is like truly remarkable. I mean, in electronics, you can never do that, right? That's extremely, extremely powerful. But the challenge with photonics is that it's sort of like having a Ferrari and you are on a dirt road, right? So you have this super fast IMC core, which can do things so fast, it's spitting out data at that speed, and then you are hitting all the roadblocks along the way, right? Yeah, so I think if we can keep processing in the photonic domain for as long as possible, I think it's possible. Maybe then there is a pathway. We have a U project on that. But if it is as part of the heterogeneous architectures that I talked about, you're always going to be limited by something else. And unfortunately, in photonics, you always need some photonic electronic conversions, which are not that cheap either, right? And then you need on-chip lasers and whatnot and all this stuff, right? Yeah, but as a core, it is so fascinating. I mean, it's like incredibly fast.
Thanks.
Yeah, let's thank Abu once again.